This is Chapter 7, Section 5, Using Proportional Relationships. Your objectives are to use ratios to make indirect measurements and to use scale drawings to solve problems. Don't forget to write your essential question, and when you're writing your summary, make sure that you make an effort to draw connections between this lesson and past lessons if you find them. So this is the first vocab word that we need to talk about, indirect measurement. An indirect measurement is whenever you're using formulas, similar figures, and or proportions to solve. So I have an example here. I have a tree, picture of myself, and I'm trying to figure out how tall the tree is based on knowing my height and my shadow length and the tree's shadow length. And then you can set it up as a proportion. So the tree's height and my height both go in the numerators. The tree's shadow and my shadow would both go in the denominators. Please make sure that if you get dimensions that are given in both feet and inches, so if I said that I was 5 feet 2 inches instead of 6 feet tall, then I would have to change that all into inches or all into feet. Here's your first example. It says, Tyler wants to find the height of the telephone pole. He measured the pole's shadow and his own shadow and then made a diagram. What is the height, h, of the pole? We know that Tyler is 5 feet 9 inches tall. We know that his shadow is 7 feet 8 inches tall. The height of the pole is what we're looking for, so that's labeled as h. And then we know that the shadow that the pole is making is 38 feet 4 inches. Now, first thing we have to do is convert everything to inches. So I've got AB, which is 7 feet, and I'm going to multiply 7 times 12 to get my feet in inches, and then I need to add those 8, which is going to give me 92 inches. I'm actually going to label that right here. This is the measurement that we're going to use when we're writing our ratios. And then BC, which is his height, is the 5 feet times 12, because I want that in inches, plus the 9, which is going to give me 69 inches. I'm going to label that right here. So we're not going to use these numbers anymore. And then we need to figure out what this is in inches, so that's FG, which is 38 feet times 12, so we can have that in inches, plus the 4, which is going to end up giving us 460. And again, that's the number that we're going to use instead of that one. Now that we have these new values, we need to check to make sure that our triangles are similar. And if you notice the height of the, what is this called? Light pole? Telephone pole. The height of the telephone pole and this angle that it creates going across the ground is going to be horizontal, the height of the pole is vertical, so it makes a 90-degree angle. And then same thing for Tyler, he's standing up on the ground, so vertical and horizontal, that makes a 90-degree angle. So we have an angle, and we know that the sun's rays, so if I have my sun right here, are going to be parallel no matter what. So they're always going in the same direction. So we know that these two lines are parallel. We know that the pole and Tyler are parallel, those lines, because they are both going vertically, and then the ground is obviously going in the same direction as itself. So my triangles are similar. And now we need to set up our proportion. So we have BC, which is 69, over our height, which is what we're looking for, is equal to AB, which is 92, over the 460. We're going to use cross products to figure out what our answer is. So h times 92 gives me 92h. And then I have 69 times 460. And if I solve that, multiply these, and then divide by 92, I end up getting the height is 345 inches, because that's what we converted everything to. If you wanted to change that back to feet and inches, you would divide that by 12 to see how many feet are in there, and you would get 28 feet and 9 inches. Again, we have this extra practice problem. I highly encourage you to go back into your textbook, find page 507, work out number 28, and then look up the answer in the back of the book to see if you've gotten it correct. This is the next two vocab words that you need to know. A scale drawing is a drawing that's either larger or smaller than its actual size in real life. So this is a scale drawing of my father inside his truck on his way to work. He's obviously not that tiny, and neither is his truck. So this is a scale drawing of something else that's represented in real life. A scale is the ratio of that either smaller or larger thing to its corresponding actual length. So on a map, you can have a ratio or a scale of 1 centimeter to 1,500 meters in real life. And then I have a little note here. Remember that proportion may compare measurements that have different units, so you have to be careful, be aware of that. This is allowed, but if you have two different units within the same measure, like we did when we were talking about our height for our flagpole, if we had feet and inches, this needs to be converted to 1. But if I have centimeters being compared with meters, then that's okay. Here's your next example. It says, on a Wisconsin road map, Christian measures a distance of 11 1/8 inches from Madison to Wausau. The scale on this map is 1 inch to 13 miles. What is the actual distance between Madison and that other place? To the nearest mile. All right, so what we need to do is create a proportion comparing the distance and the scale. So the distance is 11 1/8, and that's on the map. I don't know how far it is in real life, but I do know that that's 1 inch to 13 miles. So this is the miles that I'm looking for. Again, we're going to use cross products. So 11 1/8 times 13 is going to be equal to 1x. I have x equal to, and then if you want to change that to an improper fraction, this is going to be 89/8, so that's 11 times 8 plus 1, times 13, and then you end up getting, multiply that and then divide by 8, you end up getting 145. So these two cities are going to be 145 miles apart. And this is approximate, this isn't exact, but that's the way we speak when we're talking about, I should change this to an approximation sign, when we're talking about how far something is. We round to the nearest mile. So this is 145 miles. And it says nearest mile. Oops. Next example, we're talking about Lady Liberty holding a tablet in her hand. The tablet is 7.19 meters long and 4.14 meters wide. You are being asked to make a scale drawing. If you were going to make that scale drawing 1 centimeter to 0.75 meters, what would be the dimensions to the nearest tenth? So that's what we're going to figure out. Here's my Lady Liberty there. So we've got the length, which is 17.19. Oh, sorry, just 7. We'll change that. 7.19. That's a 1. And our scale, which is 1 over 75 hundredths. And I'm going to go ahead and make the other one too for the width. So the width, and then we have 4.14, and that's going to be equal to, again, the same scale, 1 over 0.75. Again, just like the others, you're going to use cross products. So I'm going to multiply across. I have L times 0.75 is equal to 7.19 times 1 is just 7.19. Divide both sides, by 75 hundredths, I end up getting the length equal to 9.6 centimeters, and again, that's approximate. It's not exactly 9.6. Same thing here, we're going to use cross products again, so this is 0.75W equal to 4.14 times 1 is just 4.14. Divide both sides by 0.75. 0.75. These cancel. I end up with W equal to approximately 5.5 centimeters. And so now we have our length and our width. Extra practice, please look at page 491, problems numbers 15 and 17. Check your answers in the back of the book because that's where they are. And you can check to make sure that you understand what's going on. So this statement and these ratios are comparing similar triangles, and this is actually related to this. If you check this out, it shows you kind of a proof of what the information is that they tell you in this theorem here. What you need to know is that if you have two triangles or any two shapes that are similar, you can make ratios from them. And if you have a ratio, you know that the perimeter, the change in the perimeter is going to be the same ratio. The change in the area is going to be that ratio squared because area is 2D. It's a dimension that's squared. So this is what you need to have memorized. If you have a change in the shape, but the shapes are similar, the ratio for the shape is going to be the same ratio for the entire perimeter of the shape. The ratio for the area of the two is going to be whatever that number is squared, whatever that fraction is squared. So here's our last example, and I'm going to kind of explain what we just talked about on that previous sheet. I have triangle LMN and triangle QRT. They want us to find the perimeter and the area of QRS, sorry. They give us the perimeter and the area for the larger. We need to find the perimeter and the area for the smaller. The first thing that we're going to do is we're going to create a ratio. So the ratio is going to be 13 to 9.1. And notice I started with this one because in my directions it says that it names LMN before it names QRT. Now that we have our ratio, we need to remember that we have both the perimeter and the area to look for. Perimeter and area. Now we said the perimeter was going to be the exact same, so the ratio for the perimeter is still going to be 13 over 9.1. The ratio for the area is going to be 13 over 9.1 squared. And then we can set those two numbers equal to the missing information that we have. So the 13 was a larger triangle, and the perimeter for that triangle was 36, so that's going to go here. And then the value that I'm looking for, the perimeter for the smaller one, is going to go in that missing spot right there. The area, again, the larger triangle was in the numerator spot, so the area for the larger triangle is 60 centimeters squared, and then the area for the smaller is what I'm looking for. Cross products, just like all the others that we were working on, 13p and then 9.1 times 36. And then if I multiply those and divide by 13, I get p is equal to 25.2, which is my perimeter for the smaller triangle. Here I have, and then I'm going to actually distribute this too, so that's squared and then that's squared down there. I distributed it to the numerator and the denominator. So I have a times 13 squared is equal to 9.1 squared times 60. And if I multiply these two values together and then divide by 13 squared, then my area ends up being 29.4 centimeters squared. So again, the part to remember on this one is that the perimeter has the same ratio as your shapes, and the area is going to have whatever that ratio is squared because it's area, so it's a two-dimensional space. Extra practice can be found on page 492, problem number 19, and again, you can check your answer in the back of the book to make sure that you understand what's going on. So if at the end of this lesson you understand everything that you're supposed to, you should be able to answer all of these questions. Number one, what should you do, if the dimensions are given in two different units? 2, can a proportion compare measures of different units? 3, if two triangles are similar, what do you know about their perimeter and area? And then that's all I got. So if you have any questions, make sure that you either watch the video again and or write them down so that we can talk about them in class.